a laptop?
Oh, yes, it does work.
Okay, not end meeting for. Whoa. Okay.
Okay. Now you only now told me that I'm the co-host. That's only a little bit late. That is the correct thing. Everything displaying. Everything's displaying. Splendid. We're only 7 minutes late. That's good. So yeah. So hello everyone for my talk about my PhD progression talk. So essentially just on everything that I've been doing this last year and maybe vaguely some plans for the next two. The title is slightly different from the actual announcement I sent out, which was, I think, mathematical properties of loss functions. This is differentiable logics for neural network verification. This is still the same name. It just reflects better a little bit what I'm actually going to be talking about, but we will be focused on loss functions for neural networks. Does this work? Yes. So let's just start briefly from kind of how I got to even look into it and why. So the initial plan was essentially to look at loss functions for neural networks as a whole, to look at their design space, how people design new loss functions, what are the desirable things for them, why they design new ones, etc. So typically with loss functions, we have kind of a set of commonly used ones that are just used all the time. A good example is cross entropy, and they just appear because they perform really well. Now people do come up with improvements to these, usually for specific problems. There was a paper for improving cross entropy when there is a lot of missing data for some labels, etc., etc., etc. So these are generally very specific things. And one approach to designing new loss functions that I'm actually looking at are constraint-based loss functions. So loss functions that we start out with a logical constraint that we want the neural network to satisfy. This can be robustness. This can be just anything that I can express as a logical constraint. And we want the neural network to satisfy it. So we want to figure out a translation from the logic to a mathematical loss function. Then using that loss function, we can use that to train the neural network to satisfy that constraint. And this is why this is connected to verifications, and this connects to kind of the idea of continuous verification. If we didn't verify the neural network, if it didn't fulfill the property, we can train it now with this kind of loss function, and ideally it should work with the new property. So we can look vaguely at the loss function, not too closely. There is a lot of maths in this presentation, but on most of it, we don't actually have to look at it very closely. This is essentially just here to show what a loss function is, but in general, loss function wants to take the expected output of a neural network for some input and wants to take the actual output, compare them, and penalize the function somehow. So it will update the weights if it failed to classify it correctly, and that's how the neural network will learn. So that is essentially why we are using loss functions. So the idea here that the name differentiable logic is essentially a name for the translation. So when we have this logical constraint, we want to translate it to a function. So differentiable logic means essentially finding the translation from logic to a differentiable function. This is a very misleading name considering the logic itself is not differentiable. The function at the end is differentiable, but this is what is used in literature. So we're going with differentiable logic. Now, the best way to really explain it is through examples. So for the sake of examples, we're going to first look at very small formal language. So this is, you can think of it as a very, very small fragment of first order logic. We have some terms. The terms are variables or they are constants. We have atomic formulae, which are comparisons between terms. So we can have t less than equal to t prime, for example. And then we will have conjunction and negation as well. This creates our small little tiny language. And we can call those phi's in the language. Yes?
Will you take questions as you go, or?
I can take questions like that.
it would be good here. You say only variables or constants. So your atomic formulae are only defining essentially lines and hyperplanes. You don't have terms. I mean, you said, sorry, you don't have compound terms.
You don't have additional multiplication.
Sorry?
You don't have additional multiplication. Or...
That wasn't, I think that wasn't considered anywhere. Mostly these constraints are expressed without additional multiplication. That could be added.
Okay, so at the moment I can have x equals c essentially as the only interesting or
yes, but this is
so
this is a very much
regions.
reduced format, and this is because one of the translations that I will be talking about looks specifically at atomic formulae like this. A lot of the other ones will actually kind of completely ignore this and just assume they exist. And then there is an oracle handling everything there.
Oh, okay.
That's why there is not too much else going on here. This is kind of more of a sample thing to show everything.
I don't think any of the results in this would change if you added additional multiplication.
Yeah.
Or if you added.
No, I would. The reason I asked is twofold. Lots of my questions, if I ask them, will be out of ignorance.
No worries.
But partly as well, understanding networks as classifiers and therefore as things which are partitioning a larger space by chopping out regions, or is if the language for doing that is simple enough, it might actually be tractable, or at least you get a better sense of what the regions being characterized actually are as kind of polyhedra or whatever. So
okay, so from the language, we essentially will want to have an interpretation functions that we will note by those double bars that comes from our language to some target domain D. The domains will be changing. So it wants to translate from that, and it wants to give us a result from that constraint. So the first example is DL2 based on the DL2 paper. That is, I believe, differentiable logic for deep learning, or the other way around. I can never remember what the actual name is. So we have a translation. It goes from our little language to 0 to infinity. That is the domain that it will map everything for. 0 is true, and everything else is means the constraint is not satisfied. So this first starts with translating the atomic formulae. So it translates these comparisons. We have less than or equal, just going to a maximum like this, and we have not equal with a constant and an indicator function. And then it translates addition as simple, it translates conjunction as addition. Now, it does not have negation here defined, which was in our small language, and that is because it doesn't have negation defined on constraints. So the way the negation works here only is that in practice, you push it inwards to the atomic formulae, and it is defined for the atomic formulae, which are these comparisons and all of the other ones. So greater, equal, etc., etc. This is mainly because of the domain. Well, this is because of the domain, since 0 is a constraint that is satisfied, is mapped to 0, and all of the other ones are mapped to the rest of the interval, which makes it impossible to map the negation. Now, this is also to note that having that translation, we can have the kind of more functional translation easily once we've looked at it. And I just mention it because I will be assuming sometimes later that I already have it, but I won't be explicitly putting these in.
Natalia, maybe it makes sense to go 2 slides just before this slide and tell everyone that here is 0 and 1 almost zeros. So if something is false, you want to penalize, and so you give non-zero value. So for example, that's why when you read max t minus t prime, so if we just have a look at one of the lines, Natalia, you just
yes. If we go here, then essentially speaking, we want the max to return a larger value if this is false. If t prime is actually less than t, we want this to return a larger value when it's false, because we want to penalize the neural network. The same goes for the indicator function, which will return 1. So this will be true if this will be larger than 0 if these are equal, and we want to check if these are not equal. So we want to penalize for that.
So we should read both the valuation domain D of the valuation function as measuring the extent to which something is badly false.
Yes, here, yes.
Okay. Okay.
Now, another kind of differentiable logic translation that I looked at is based on fuzzy logic. So a few words just about fuzzy logic itself is that fuzzy logic works with values in between true and false. So we have an interval 0 to 1, where 0 is an absolute truth, 0 is absolute false, and 1 is absolute truth. And the values in between are partial truth, essentially variable degrees or partial truth. Now, with fuzzy logic has an advantage of being just wildly studied. So we started with one of the typical translations of conjunction based on Gödel that goes just to a minimum. And now this is important here that we are assuming that the atomic formulae are just mapped to 0 and 1 beforehand. We don't know how, they are just handled. Because this approach kind of focused more on the fuzzy logic itself and on the logic part, instead of just looking at the atomic formulae, like the previous one. We also have a negation here. Thanks to the domain looking like this, we can have 1 minus. So 1 is absolute truth, 0 is false, not satisfied, and the values in between are partially true. Now, there are a lot of other examples in logic. These are some of the more common types of definitions for conjunction. So first we have Łukasiewicz. This is fairly simple in that it's a maximum of this term and 0. I think I have one additional parenthesis, so ignore that. We have Jaeger, which is slightly more complex in that it doesn't look as pretty anymore. But it is still a maximum between this larger term and 0, with p larger than 1. And we have a very simple one that's just product-based. It has conjunction as just multiplication. All of these have the same negation as the previous one. So all of them have the same negation, essentially, and they all map to 0, 1. So these are just different ways to translate conjunctions here that will behave differently when it comes to the resulting loss function. And now for the last one, there is a lot of stuff on this slide, so let's ignore it for a little bit. Because this paper was essentially one of the motivations on why I kind of looked at this approach at all. The title is Signal Temporal Logic, and that is because this paper was actually a reinforcement learning paper that used signal temporal logic. Here, it's mostly just a name left over because I have translated everything here to work with our fragment of logic and first order logic. So I'm not going to go too much, at all, into signal temporal logic and temporal logics as a whole, despite some of the work I put into that, because that is not going to be too relevant. To actually compare this to the other ones, we need to work in a similar type of logic. And there is also the problem of trying to use temporal logics with neural networks. This is generally not something that is typically done. And there is a problem with the time domain, essentially. Just briefly, the problem with the time domain is that it is very specific and that it's ordered, and that being ordered is intrinsically a part of it. So all of the training that uses temporal logics assumes at some level that the performance of what we're training has some correlation with the passage of time that is ordered. So that's why it's not really trivial to apply that to neural networks. And this is, so this entire thing here is just looking at first order logic fragment here, not the signal temporal logic that's only in the name. And essentially this approach is also slightly different from the other two, in which they started from defining properties. They started from defining a list of mathematical properties that they want the resulting function to have, not looking specifically at the logic. And then they designed a translation of the conjunction. So going a little piece by piece, first we've got the domain that's minus to plus infinity there. That's the kind of largest one. We've got the conjunction of M elements, and that is because this translation is not associative. So we have this kind of translation, and we'll denote it by this larger conjunction in M. And then we can look at the actual translation of conjunction, which is this entire thing. This is far less friendly to just looking than all of the previous ones, considering it has a men here, it has an a-tailed here that is separately defined to not clutter this. It has some other constant as well. But generally speaking, we don't need to look too much into this. We don't need to focus too much on the maths. I will be discussing mathematical properties of it, but I will be discussing stuff that's already there. So we don't actually need to look at the maths too much. You should note that there is a negation, and negation involves just flipping the sign there at the bottom of the page. That's possible because of the large domain that we have from minus to plus infinity. So essentially here, true will be anything that's larger than 0. So this will, this works slightly different than a typical loss. Now, one thing that also has to be discussed is that typically these functions, the functions that we get from all of these translations, are not used on their own to train the neural network. They are used in conjunction with some other function. So we're essentially have a plus of, let's say, cross entropy loss and this loss just scaled properly. And this brings a little bit of a problem because, as we've seen, the values that the losses take are wildly different. So the last one, for example, goes for values from minus to plus infinity, so we can get very large values. Cross entropy, which is particularly used for training, will go to 0 and 1, which means that larger values will completely overwhelm the other ones in training. So they will need to be properly transformed or scaled down. The problem the other way around can be with fuzzy logic, which, since it uses an interval from 0 to 1, can have very small values. And if we are using a loss function with larger ones, these can become almost completely irrelevant in the training. So this is something that has to be noted. Now, the last translation, the one that has the very large values, didn't pay attention to that because it was intended for reinforcement learning. It was intended to be used on its own, not with anything else. So this is kind of my problem here with trying to use this for neural networks. But now we can actually look at the properties. So one of the original goals that I had was to kind of look at what is desirable in loss functions. And this kind of brought me to the approach that was there in the SCL translation, which starts from going from listing all the properties that they want the loss function to have, the translation to the loss function to have. So I'll just go through them, and some of them are very trivial, so I won't spend too much time on them, and some of them are more interesting. So yeah, we're going to start from soundness and completeness. So before we even start with the definition, we need to know that the language has some interpretation of the formulae to true and false, and that we have a part of the domain that maps to true, and we have some notation for that. That's the D true. And so once we have this, we can define soundness in that the deal is sound if for any constraint, the value produced for that constraint belongs to the part of the domain that is true, if and only if the constraint is true in this interpretation. So this is very much dependent on the domain. So it will be different for each of the translations. So we can now look essentially at each of the translations. So starting from DL2, we go from 0 to infinity. So the constraint is satisfied in that the constraint is true, if and only if the value is 0. This is why we couldn't have negation in the language. It's because it's not equally mapped in there, so we can't actually have a negation defined for anything else in the atomic formulae. Then we have the fuzzy logic, and this is a little bit of a complex problem. Fuzzy logic operates on the assumption that we have partial truth values in the middle between 0 and 1. A problem with this is that we want, for neural network constraint purposes, we want true and false. We don't want partially true. Partially true is still not true for us. It's still false. So in that sense, we get this that we have here, which has 1 on this end, which means that there is it's an absolute truth. We look at the constraint is satisfied only if it is absolutely true. Now, the problem with this is that we lose a little bit of the, well, quite a bit of the expressiveness of the fuzzy logic, because we're essentially abandoning the idea. We're trying to force it to be, to stop being fuzzy, essentially, to stop having partial truth values. We could go around this, possibly, well, we could go around this. There could be a different solution if we actually formulated constraints that took advantage of fuzzy logic, but we'd have to find constraints for neural networks that want partial satisfaction, partial truth, and take that into account. And Soundness for the last translation, which is the STL translation, is just that it is true. When it is true, the value is going to be larger than 0.
So in line 5, should that read calligraphic I of phi equals true if and only if?
It should be true or absolute true. So 1 in fuzzy logic denotes a kind of absolute truth. So this is true, but this is completely true. Yes, it should be true, essentially. We don't want, well, yeah. Next thing is commutativity, idempotence, and associativity. Won't be going into too much detail because everyone vaguely knows what these are, but it is important that associativity is not part of the original set of properties that were defined for that STL metric, because it will contradict one of the ones that are later and that were deemed more desirable. So that's why, yeah, we added it because it might be desirable for some of the other ones. Now we have weak smoothness. Let's mostly ignore the definition. It just means that we want things to be smooth. We can guarantee that they are smooth at points with unique minimum. It's just because with the other properties and everything, full smoothness couldn't be guaranteed. So we've gotten weak smoothness for the STL translation. Min-max boundedness is just so that we can ensure it's closed in its the closure in the domain of all of the translations. Scale invariance, we would like ideally to have similar behavior regardless of the scale and regardless of the values in question. And now we get to the kind of most important property, the property that motivated that translation, and that's the shadowlifting property. In kind of more colloquial terms than this mathematical equation, this property wants you to reward even partial improvement. So when we have a conjunction, we want the value of conjunction increase if the value of one of the elements in the conjunction increases as well. So if one of the elements gets larger, we want the value of the interpretation of entire conjunction to also increase. This way we can reward the neural network for even partial improvement, even if the conjunction is still not true. It's false, but it's slightly less false. So we want to reward it, essentially. And now comes the kind of comparison of all the functions. So let's go through what's actually in the table. We've got the first column, which is the DL2 translation. We've got all the 4 fuzzy logic translations, Gödel, Łukasiewicz, Jaeger, and product. And we've got our STL translation. We've got their domains and we've got the properties. So if they have a number, that's just notation for me that this was proved and discussed in the paper. So for the STL logic, let's start with this. Essentially, this was designed to fulfill these metrics, aside from associativity, as I mentioned. Now, the problem with associativity is mainly because associativity combined with idempotence prohibits shadowlifting. So you cannot have the 3 of these at once. I actually don't have an example there, so I can just write that somewhere. So if we had conjunction of 1 plus t, 1 plus t, and let's say we also had conjunction 1 plus t, if these were idempotent and associative, this would be equivalent to the value of this conjunction, essentially, if they were idempotent and associative. But with shadowlifting, we'd like the value for this to be larger, because the value of the individual conjuncts is larger than this one. So this is kind of more of an example, just to kind of quickly illustrate it. But we can also see that we can have two of these at any point. So we can have shadowlifting and idempotence, as here. We can have shadowlifting and associativity, but without idempotence, or we can have shadowlifting and associativity without idempotence. Actually, and we can have idempotence and associativity as well, without shadowlifting. So we can only have two of these.
But on your account of the example, it suggests that idempotence is the one you want to give up, because that's the one that says ignore multiple contributions of a constraint rather than let it magnify.
Well, it only prohibits it if there is both idempotence and associativity. So it depends essentially on which one of these one prefers. So that is a kind of a larger question. So for example,
yeah, but I was looking at your
Yeah.
example you gave, and you said it doesn't satisfy shadowlifting. Shadowlifting seems an important idea. If we improve our knowledge of something on any axis, we ought to improve knowledge of its conjunction. The thing at hand that makes that objectionable if you accept associativity, okay, is the failure of idempotence, because you're not counting the contributions of each component properly. And it seems like that would be a more obvious candidate to abandon, but perhaps I'm wrong.
it very much depends. So essentially here they decided to abandon associativity because they decided it was less important. For all of the fuzzy logics, for example, associativity is one of the things that is necessary because these are based on triangular norms, which just are defined by having associativity as one of the, well, that's part of the definition. So these decided that associativity is more important, idempotence not so much. So that is actually one of the questions that I will be looking at. Well, I will be looking at the consequence of not having associativity. In that, does it, if it's not associative, does it preserve minima, which is important for training. Essentially, if I had two things that with associativity would be the same, but without associativity, don't get the same translation. Does it preserve the minima? That's one of the things that I'll probably be investigating. But that's one of the things about this is that this is not a finite set of properties. This is just a set of properties that we've decided are desirable, but they can be added, they can be removed. And there is a question of which ones are actually desirable, because normally when we look at loss functions, there is some consensus of what we want, but this mostly boils down to we would like them to be convex, we would like them to be differentiable, continuous, depending on what we can actually achieve. But there is not much else when it comes to kind of a uniform thing of what we want from things. Like we'd want associativity, commutative, and idempotence so that we are sure that we can write a constraint and not be worried about whether different ordering of the things in there would change the result. That's for that as well. Trying to think what else is interesting in this table. One of the things is that some of these properties are dependent on domains. Specifically, for example, there is scale invariance for, there's min-max boundedness for product. This is essentially just multiplication, but this is a yes, because the domain is 0, 1. So it will be contained. However, for the other ones, this would not have worked if they decided to use product. So the domain ends up being quite a large part of the decision when it comes to creating the differentiable logic translation. So now really we now have a uniform way to express the differentiable logics, and we have the table of properties, unless somebody else has questions about the properties still. No, okay. So we have the table of properties, we've had how they generally compare differently. So that allows us to kind of look at what we actually want from a translation like this. what are the choices that we have to make if we design a new one and what we have to pay attention to. So the first kind of attribute that we have to consider is expressiveness. So the problem with the negation and the deal-to translation falls into that, in that we don't have translation of negation for entire constraints. We have them for atomic formulae, and that only works because we've explicitly defined negation for atomic formulae. For the other approaches, this wouldn't work unless we also assumed we have an oracle for translating that. There is also, for example, that also encompasses the problem with the fuzzy logic, where we are trying to say what is true and what is false when we are starting to work from something that assumed partial truths. And that changes the way the metric behaves in a way, because it stops being symmetrical. We say one is the true, the rest of this interval is false. And that kind of marries into what I started talking about with the properties, in that they're not essentially a full set. They're something that we can change, we can edit. So there is a question of which do we actually want to keep, which do we think are important. There is also the thing that actually the properties, as we've seen, are mainly influenced by how we decide to define the logical connectives. So the negation was very clearly influenced by the domain. So it was flipping the sign when the domain was entire real numbers. It was 1 minus the value if it was 0 to 1. And we had problem with the DL2 case because of how the domain was defined. But with conjunction, there is quite a bit of leeway, and that we can see here that for the 4 different fuzzy logics, which all have differently defined conjunctions but the same domain, the translation for conjunction was completely different. And the properties and the behavior mathematically is completely different. So this is one of the very important choices when it comes to that. Let's get back here. And the last thing, which I haven't really mentioned before too much, is the practical aspect, which is just training the neural network, because this was very theoretical, but it does produce a loss function that is supposed to be training a neural network. And there is, for example, we would not want transcendental functions or case splits just because they are costly to train, more costly than other functions. And they existed especially in the SDL translation, but they also exist. Case splits exist in a few other fuzzy logic translations that I didn't paste here. But yeah, these essentially would create a function that might be mathematically really nice and really, really great. It has lovely properties, but it also takes far longer to train. It's costly. So this, yeah. Oh, sorry, that's right. This really brings me to what I'm intending to do over the next either 2 years or sometimes in the course of, let's say, next few months, etc. So the first thing would be to do some sort of experimental evaluation on all of these loss functions. So take some constraint, translate them in different translations, apply it to train neural networks with it, compare how they perform when it comes to accuracy, robustness, etc. See if there is something very clearly different there. They shouldn't mostly be, but that still needs to be done just to compare and see, because I don't have these results yet. The second thing is the thing I mentioned with associativity, and generally analyzing some of these properties to see what we want, and especially with whether non-associativity is a problem when it comes to training, whether it does something to the minimus. One other thing will be essentially getting a new translation for writing a translation for a more for a high-level language, essentially, and just getting a new translation and getting this written up for something more substantial than the small example that I've done there.
And to give an indication of the size of these constraints, for even in this, for example.
The size of what?
I mean, how big is the conjunction, for example, for specifying robustness for MNIST?
Well, that really depends, but it will be. For robustness, I don't actually think I have an example anywhere. But generally speaking, most of the constraints, either if there might be robustness or there will be things involving multiple classes. The conjunction itself is large, and then the entire thing is just going, it blows up really quickly, considering the definitions. So they're not small. But I don't think I have an example right now here that I can open. Yeah, and the last thing that's maybe somewhere for in the future, well, that's maybe somewhere in the future, depending. It might be formalization of the translation and some of the properties, but that is still up in the air. So yeah, thank you. That's the end. Any questions?
Good.
Oh, I haven't seen that. Yeah.
No,
So
that's
go
a plan.
ahead.
Oh, right.
Not a question, it's a clap.
Ah, that's a clap. Okay.
So, okay, so no, I don't. No, I'll draw a question.
That's great. That means I explained it.
Can you give insight? Sorry, I'm going to harp on this, and you can tell me to shut up if it's annoying. What does the 2020, and I have already forgotten the author's names, the SDL paper?
The SDL paper.
What is the argument for idempotence?
I don't think
Over
they don't give any argument for why one is over the other, to be honest. So they just say that this is the one that we want to use.
Because I'll say why I'm on the hobby horse about this is from a logician's point of view. If you want to consider non-standard logics or non-standard interpretations, then one way to kind of measure how far you diverge from orthodox interpretations is by looking at what structural rules of the logic you hang on to. And the one that almost nobody wishes to give up is the exchange rule, the commutability of assumptions in the context. Whereas it's very typical to abandon contraction, which would correspond to idempotence. So from the symbolic side, rather than the numerical side, a natural condition to abandon before commutativity or associativity would be idempotence. And so I'm curious that there are examples where, no, that's considered really important.
No, they haven't had much when it comes to reasoning behind some of the kind of more basic properties. They mostly focused on shadowlifting, and the rest was kind of there, defined and a little bit unwanted. So yeah, it was surprising comparatively because everything else does keep associativity. But
James, thanks for the comment. We wanted to investigate this anyway, but your comments actually focus our attention that this is something to look at sooner rather than later.
I mean, there may be very good reasons for it. I'm curious if the paper that itself proposes it doesn't kind of have a good account of
To me, it
that.
wasn't also so obvious why you would necessarily prefer idempotence, give up idempotence, or rather give up keep idempotence.
I mean, people are unlikely to write idempotent. That's the other thing, is people are unlikely to write specifications, constraints where you need to actually apply idempotence.
that's true.
It's unusual to write the same condition
multiple times.
times in the same step.
Whereas associativity typically would be one that we'd actually want when people are writing it.
But you might imagine complex compound constraints which contain within them repeated occurrences of atoms, which might cash out as that atom is making more of a contribution to how you think that influences the truth or otherwise of the constraint. And that multiplicity is what you're abolishing with idempotence. And
Is that not either a user? Is that not either a usability flaw or a usability feature? If somebody doesn't know about the lack of associativity of the logic language they're using, then they can be disappointed by the end result, or if they know how to use it properly, if they know that if associativity actually will mean that the minima of the loss function is somewhere else, because I care more about that term than the other term. Maybe it's a feature, usability feature.
Indeed, so you could prioritize the order in which you consider the constraint.
Yeah.
Yeah, interesting. Yeah.
So I mean, the motivation for a lot of this, well, the practical motivation is to incorporate it into vehicle, which I've shown. But we have a really expressive high-level dependently type language. They have quantifiers over tensors, and you don't have to write these low-level constraints. You write something high-level and concise, and then it automatically translates it down to something like this. So yeah, so the usability is a big, like the user gets what the user understands at what they're writing at a high level, which may not even have a conjunction, may not even have any conjunctions in, but maybe normalize down to conjunctions. We need some guarantees that they're not going to get weird behavior from writing something obvious, but in the translation gets lost.
And again, if you think about dependency, the obvious thing to abandon would be commutativity, because you want to say that subsequent conjuncts might depend on the presupposition of the preceding ones. So in this design space, both for usability but also expressiveness, there might be biases towards a particular direction or particular set of choices. And I guess that comes from the original vehicle proposal rather than anything else, if that's the intended target.
Yeah, I would also note that one place where you do lose exchange, at least in a sort of unrestricted way, is dependent types, right? So when you have dependency or exchanges, you're only allowed to exchange as long as it's not dependent on the previous one, right? In the context.
Yeah.
So in this sense, maybe it is something that you can give up.
But again, commutativity rather than associativity.
Yeah.
Interesting.
I guess Natalia was also just saying one last thing. Natalia's glossed over it, but actually we're really struggling with. It's not just a translation of the logic of the logical formulas; it's actually a translation of propositions as well, which is really difficult. I mean, we had a hack at it this morning, thinking, "Oh, we'll solve it." But actually, if you've got a limited, if you're restricting your domain so that you're bounded, it's really difficult to come up with good translations of propositions of less than equal to and strictly less than. And the DL2 paper, which is the only one trying to handle it, fudged it massively and had really unsatisfactory non-monotonic something like this. This was the famous tick that we were talking about.
Oh, okay.
So this is the translation of strictly less than. So if you're exactly equal, you have a massive loss penalty. And if you're actually just a little bit greater than equal to, suddenly your loss isn't as bad as if you were equal. So it's the whole translation is non-monotonic. It's deeply unsatisfactory. So yeah, it's,
I guess the big thing to say is that the whole problem, and that's why it took Natalia so long to compile it. Is that in majority of cases, the problem hasn't been looked at by logicians, but by machine learning people. So this translation, for example, just someone wanted to hack quickly so that they could translate constraints into loss functions and train and get results, evaluation and publication. So this stuff is not, this was quite influential paper because it was one of the first to give a generic translation of a logical language into loss function. But yet people haven't looked into it in a principled way. It was almost like every machine learning paper hacks it a little bit because in their domain it works. And that obviously very interesting, therefore, to see Natalia's dissertation mature, because it potentially can reveal quite a few things if you look at things in comparison.
Impose structure on chaos.
And then logically as well, if you look at things logically rather than from a machine learning perspective.
Yeah. Okay.
Yeah, no, it's difficult. For some time of the first year of PhD, already felt it, walking in the woods, thinking that,
Yeah.
okay, because we only knew about this, and we knew about
The STL one.
signal temporal logic, and the syntax was very different, application domains were different, loss functions were different.
The fuzzy logic one is very new, actually. Well, this paper is from this year, essentially.
The
So we
fuzzy
only
logic
found it.
helped us to put everything in perspective, because then we could see common pattern in these differential logics. Even the
Yeah.
very term differential logics, different people use them in papers, but there was never.
They also use different
Discussion.
terms to describe this. So differentiable logic is the term that I've seen the most often, but it isn't an actual single name that is used everywhere.
I have a different, very nerdy question about fuzzy DL. Is, in a sense, all the others you present identify the half line as, or parts of the half line as true, whereas this is opposite to that. So what would happen, as it were, if you renormalized fuzzy DL by exchanging 0 and 1 and just looked at the behavior of that? I mean, formally the properties wouldn't change because you would, quote, just be dualizing, but it might be easier to understand the relationship between this one and the others if you took 0 as true.
If I took 0 as true, that one I haven't actually thought about. But yeah, this is a very good point.
What
Well,
alternatively
it
passes
might be a terrible point because in a sense, one is sitting in the right part of the half line. But given the way you introduce the other ones as there being a quantitative measure of falsity, reposing this so that it was also a quantitative measure of falsity, with 1 being it's as false as it can be, and 0 being it's not false at all, i.e. it's true, might allow a fairer like-for-like comparison. I don't know.
That's probably true, because what happens is in every paper, it depends whether people use the same function as reward or penalty. And depending on that, I think James is absolutely right. It's a matter of flipping in this case, because it then boils down to your implementation, whether you reward or penalize when you actually feed the function. So
Indeed,
this
a
is something
minus
tricky.
sign is a very powerful weapon in the mathematician's arsenal, but requires to be used with care. Yeah.
So this is actually a very fair point. It has to do with the fact that we haven't yet looked at adjustments to the application domain. That's probably right. We should.
For those people who are not just interested in training, but I mean, it's actually a strong search connection for these functions as well, in that you can use these functions to search for counterexamples for your spec, because you can look at the grade, you can differentiate them in the same way, and then you can follow the gradient to find counterexamples, which is much cheaper than throwing a full-blown abstract interpretation or SMT solver at the problem in order to first try and find some easy counterexamples. So it's not just training, but they also have implications for verification itself.
Yeah.
As you mean who those people?
No, just in general. In general, I mean the PGD people and the FGSM people. I don't have specific names, but yeah, you can take this function, you can follow the gradient of it to find false examples for your spec.
Okay, but that's only for robustness purposes.
No, for any, so that's the advantage. I mean, they do it for robust, they use it only for robustness, right? But the same techniques can be used to find counterexamples to any.
I see.
So you can generate images, or if you have or you can generate counterexamples to your spec, basically, which may translate to images or sentences or something. Your class. Yeah. Which again, efficiency, important.
Okay, thanks a lot for the questions.